This is the third video in a series about acids and bases in solution. We talked about polyprotics, we talked about hydrolysis of salts and whether each of the ions will be an acid or a base. And in this last video, we're going to talk about the common ion effect, when we add multiple compounds into the solution and they have ions in common. So we've talked a lot about weak acids and bases and their ionization so far. So weak acids and weak bases, we define them that way because they dissociate partially in solution. If you learn nothing else from this chapter, I want you to learn that strong acids and bases fully dissociate and weak acids and bases partially dissociate. Okay, so here's our generic acid, HA. When we put that in water, it will partially dissociate to make its conjugate base and hydronium. And this is called the acid ionization reaction. When we put our weak base in solution, generic weak base, in solution with water, it will get protonated partially to form a conjugate acid and hydroxide. And that's called the base ionization reaction. Ionization in water. Okay, so in this case, we're picturing just having one piece, either a weak base or a weak acid in the solution producing these ions. But we can have more than one thing in the container at the same time. So if we took that weak acid or base and we added another compound, and that compound produced an ion in common with our first compound, in common with the weak acid or base, it decreases the ionization of that acid or base. Okay, so it has an ion in common, the common ion effect. It decreases ionization. So what does that mean? Ionization is the process of the weak acid or base in water splitting up into ions. And so when we add something in common in the product, if we add more products, we're going to decrease how much of this splits up and push back this way. This should probably sound familiar. This is something we've already seen in the equilibrium chapter. Okay, so remember we talked about the different ways to shift or to stress, rather, the different ways to stress equilibrium. One of the ways we said we could stress the equilibrium was to add a product. And if we added the product, we said that that pushed Q to be larger than K, and that we shifted back to equilibrium by shifting to the left towards the reactants. So if we add one of these ions in the product, so this one or this one or this one, it will cause the reaction to shift back towards the left, and it decreases the ionization. It decreases the forward reaction. So this shouldn't be too much of a surprise since we covered it pretty heavily in the last chapter. But let's look at what the ice table will look like when this happens. So here's an example problem. So find the concentration of hydronium in a weak acid only solution with this acetic acid, and in a solution that has both a weak acid and its conjugate base, acetic acid and acetate. So adding that conjugate base is adding a product. So let's see how that changes the ionization of these two things. So let's do ice tables. I'm going to start over here so I don't run out of space. We're going to do it in moles per liter. And we're going to use our generic acid ionization equation for the top. Okay, and we'll just go ahead and set up the other one while we're here just to make sure it'll fit. We're going to do it twice. Once for part A and once for part B. Oh, cutting it close, but we made it. Okay, let's do part A. So part A, we have 0.1 molar of CH3COOH, which is a weak acid. So we know that that can go straight into the initial row of our ice table. We know that we don't include water in the table. We don't have any of this conjugate base present initially, and we have approximately 0 of hydronium. Then this is a weak acid. And so weak acids are going to partially dissociate. And since there's a 0 on this side, we're going to shift towards the right. We're going to decrease reactants, increase products, and the amount we change it by is going to be X because it's a weak acid. Add down. There we go. And then we can take our equilibrium line and plug it into our equilibrium constant. Products over reactants, X times X over 0.1 minus X, and set that equal to our K value, 1.8, 10 to the negative fifth. And when we see that this number next to the X is 0.1 and this number is to the 10 to the negative fifth, we can see those numbers are super far apart. So we're going to go ahead and use our assumption X is much smaller than 0.1. We can rewrite the reaction without this X, assuming it's super small. So X squared over 0.1 equals 1.8 times 10 to the negative fifth. And then we can rearrange that and solve for X. And we get X equals 1.3 10 to the negative third. And whenever we use the assumption, we always have to go back and check to make sure it's accurate. So we check X over our initial value above it and multiply by 100%. So in this case, that gives us 1%, and we're allowed to use up to 5% error. So 1% is less than 5% error. So our value for X is okay. All right, so step 1 is the shift, step 2 is the table, step 3 is our K value. Step 4, answer the question. The question wants the hydronium concentration. And hydronium is just equal to X. There we go. So when the acid is by itself in the solution, that 0.1 molar of the acid dissociates partially to form 1.3 10 to the negative third molar of product. All right, so let's divide our page here. And now we'll do part B. So part B, we have 2 different initial compounds. So we'll want to include both of those in the first line of the table. Okay, so we initially have 0.1 molar of the weak acid. And we also have 0.1 molar of this guy, which looks just like this one, but is missing a proton. It has a sodium instead. And we remember from the previous video that this ion is inert. And this is going to be a weak base. All right, so that means we have 0.1 molar of the weak acid and 0.1 molar, of the weak base. At the beginning, we don't include liquid water, and we have approximately 0 of our hydronium to start. When we want to think about our shift, it's a little bit more complicated now, but there's still a 0 on the product side, if you can see that. One of the products still has a 0, so we are still going to be shifting to the right, just like the last one. So we decrease reactants, we increase products, we still have a weak acid and weak base system. So the amount that we shift is going to be small, some unknown small number x. We can add down. And then we can set up our K expression using everything in the E row. All right, so it's going to be products over reactants. So 0.1 plus x times x over 0.1 minus x. And those are all to the first because we all have coefficients of 1. And that's equal to 1.8 10 to the negative fifth. We always like to try and assume x is small because that's a neat trick. And we can see that these numbers are more than 100 times apart. So we feel pretty good about this working. So we're going to assume x is small, set up our equation again. And if x is small, we can assume this x goes away and this x goes away. So we've got, actually, if we cancel out those x's, we can also cancel out the 0.1. 0.1 and 0.1 cancels. So we don't even have to bother solving the problem. We can skip all the way down to just x equals the Ka. So that seems too good to be true. So whenever we use the assumption, we always go back and check. So we check that x divided by that initial number above it has to be less than 5%. And if you calculate it, the percent error is 0.02% error. So that number is definitely less than 5. So our shortcut worked. That was a totally legal move that we just made. All right, so step 1 is the shift, step 2, ice table, step 3, Ka, step 4, answer the question, find the hydronium concentration. So hydronium is equal to x, and x is equal to 1.8 10 to the negative fifth molar. Okay, and now that we answered the question, let's use our brains once more before the end of the video. The whole point of this video was about the common ion effect. We said that if you add a product ion, you decrease the ionization. So what we just did here is on the left, we only had the weak acid, and on the right, we added some of the weak base. And that should have pushed the reaction back to the left. And if we compare the end, if we compare this reaction went from 0.1 to 1.3 10 to the negative third, and this reaction went from 0.1 to a smaller number, 1.8 10 to the negative fifth. So the number on the left is bigger. So the left situation ionized more, and the right situation ionized less. So when we added some of that conjugate base into the solution, we decreased the amount of ionization that happened in the flask. So this is an effect that you're going to be using sort of in your head. We're not going to mention it much more after this, but you should understand that when you add a product in with a reactant, it will push the reaction back to the left, and you'll see less ionization. And this is going to be a type of equation that we're using in the next set of videos when we start to talk about buffers.